Hello, students. Had a few questions from the homework section. I want to hit those out of section 5.1. First one was number 17. And the student's question was, hey, so I think I can do part A, but the subtraction isn't commutative. How come this works? Or this is really kind of screwing with my head a little bit. And, it's a reasonable thing to say because it definitely looks like the student is saying, hey, subtraction is commutative. And you'll get this as well as one of your MCs. Something similar to this. So the first part says prove something. So I want to prove something. Again, that's guaranteeing it has to be true for all the numbers. So I'm going to use just the definitions. There's actually a couple ways to prove this one. So I'll prove it one way and then I'll prove it another way. You can choose which of the proofs you like better, which I've actually enjoyed about math is I can find one that I like better. Both of them are perfectly legitimate. So I'm going to show, the first one is I'm going to start with the left-hand side and I'm going to work algebraically until I turn it into the right-hand side. Okay. So let's see here. So I would have negative, or the opposite of x minus y. Even I said negative because my brain is wired that way too. Opposite of x minus y. And now what I'm going to do is I'm going to use the fact that subtraction can be rewritten as adding the opposite. Now, again, you can look up the theorem number if you need to, but it's really the one that says a minus b is equal to a plus the opposite of b. So that's all I'm doing. Okay. Next up, addition is what I have. I have addition between two values. That addition is commutative. And so as I kind of move from here to here, this would be saying addition is commutative. Yay. And then the last piece would be to show that kind of like what we did up here, just realize there's an equal sign between them. And when you have an equal sign, it means the two quantities are exactly the same. So if you want to say the right-hand side is equal to the left-hand side, you could go that direction. Some people see this kind of like a path. You could go this direction on the path. You could go this direction on the path. The first one, we went from left to right. But now if I have a plus and an opposite, according to this, I could rewrite this as subtraction. And I just need to give a reason for it. So going from here to here is that a plus the opposite of b is equal to a minus b. So there you go. What did I do? I started with the first part. I worked my way down. I got to the second part. So again, I said that's one way that you can do it. The other way that you could prove this theorem is you could prove that things are equal because they're additive inverses of the same thing. So what would that look like? If I did y plus x just as a quantity, and then I added this left-hand side to it, opposite of x minus y, right? Then I'd really have y plus x plus the opposite of x, right? And x plus the opposite of x is 0. So I have y plus 0 minus y. And anything plus 0 is itself. That's the identity property. And anything minus itself is 0. So there we go. So what this shows is that y plus x and opposite of x minus y, those are additive inverses because when I add them together, I get to 0. So then I come over and I say, okay, well, let's try that again. This time we'll do it with the other value. So I start with y plus x. This time I add the second component here, this minus y minus x, okay? And now I use commutativity on the front to rewrite this as x plus y plus opposite of y minus x. And now here I'm going to have x plus y plus the opposite of y minus x. Y plus the opposite of y is 0 because they're additive inverses. And anything plus 0 is itself. That's the identity property. And so I end up with x minus x, which is 0. So what we're saying, and again, this is one of those kind of techniques that we may use from time to time is I am starting with the same quantity here. I'm adding something to it. And each time I end up with 0. So the two things that I added to it must be the same. So there's one and there's the other. Those have to be the same. And so that's your way of saying, because the additive inverses are unique, these two values must be the same. And that's exactly what you've got right up here in your equation. So does this prove that subtraction is commutative? No, it's cute, but it doesn't prove subtraction is commutative because subtraction being commutative would look very different. What do I mean? If subtraction was commutative, right, as you think about it, then what we should have is if I had this, here's my subtraction right there, then this should be equal to y minus the opposite of x. That would be commutativity of subtraction, because here's the subtraction, and then all I do is swap those and swap these. And what we're saying is, hey, that's not actually true. And we can see that from what we had to prove here, that this is not true. So this fails. All right. So there's a couple different proofs. Again, some of you were saying, hey, can you show a couple different ways to do it? I think that's more than reasonable. So there you go. All right, let's take a look. What other homework questions? 19. Let's take a look at 19. Yeah, so you're just plugging something in and off you go. I guess maybe the one, if there was one, maybe part D would be kind of a sticky one because you're thinking that you always have to have a number at the end, like a quantity like that. Just remember this value A is a number. So if you were to multiply that out, you might have something like y equals the opposite of 3 times the opposite of A minus 2. And so when you get done kind of multiplying a -3 times this opposite, you could really bring the opposite out and say it's the opposite of 3. So you end up with something that looks like this. And when they say in terms of A, they're saying make sure your answer includes A in it. So you won't be able to get rid of the A as you simplify. And that's it. That's the idea of solving something in terms of A. Number 20. Yeah, I think so. It depends on how you want to do number 20. I guess I should say it that way. But let me take, so if Scott was doing this, what would Scott do? I got to get a bracelet for that, right? WWSD. What would Scott do? Let's take a look. What would Scott do? So Scott, okay, so I use this technique when I do arithmetic sequences all the time to find the number of terms, how many terms. So if I had a 3, 5, 7, dot, 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 up to whatever number it was, then I could subtract to get to my common difference. So the first thing you have to find is that common difference. So here my common difference is 2. So I would subtract 1 so that I would end with this. Okay, so I am going to subtract 1 from each term. And that gets me down here. And then lastly, what do? Lastly, I divide by that common difference. When I divide by 2, I get 1. When I divide by 2, I get 2. When I divide by 2, I get 3, dot, dot, dot. When I divide by 2 out here, I get 51. And that sequence at the end is in order. So I could tell you that the number of terms in the sequence was 51. So you could do exactly the same thing here. Just make sure that when you start, in this case, it's a -27, you're going to add or subtract in order to get back to that common difference. And that common difference turns out to be 1. So I would add something to this negative 27. Actually, you could add it to every number in the sequence, really. Add that every time, and that will add the thing that gets you back to d equals 1 would be my starting value. Okay, good question, though. Good question. All right, let's take a look. Next up, 25. Let's take a look at 25. Now, in this one, the student said, I think I got true for all these. What the heck's going on? But and maybe they are all true. So let's take a look up here. This one classifies true or false. Oh, so this is going to be an always, sometimes, never on the test, right? If it's false, show a counterexample. So again, for me, I would say show a time it's true and a time that it's false. But yeah, we could certainly take a look at this one. I would definitely say the first one looks true. And the first one looks true because x squared is greater than or equal to 0. You multiply a number by itself. You're never going to, if it's negative, a negative times a negative gives you a positive anyway, so I don't have to stress about that. So yeah, part A looks pretty good. Yeah, part C looks good too. And that's because the x squared component that's there, the absolute value of x squared is the same as x squared. That's from part A. So they're just kind of using that to make it try to look a little bit more complicated. But once you see the trick that they're trying to do, it's pretty quick. But over here, then I would just try some numbers. And for all of these, if you're not sure, try some numbers to start off, see if that helps you kind of plan a way forward. So for example, if they said the absolute of x squared, so I would say, okay, the absolute value of 5 squared. Okay, well, I know that's the number 25. The absolute value is 25, which equals 5 squared. Okay, so that actually works perfect. You can test it with negative numbers too, and that's what I'd recommend here. Test it with positive numbers and with negative numbers and see what you end up with. Because remember, the absolute value cannot be negative. Okay, it's a distance. All right, let's take a look here. And MC4. I think for if you're looking at MC number 4, the absolute value of an integer is never negative, and I just mentioned that for the prior problem as well. Does this contradict the fact that the absolute value of x could equal to the opposite of x? But just again, when you're saying it, I think the biggest thing if you're struggling with this is to go over and look at question 11 right here, MC number 11. Because the difference is in using these symbols to say, is it negative, is it subtraction, or is it the opposite, right? So any number you put down, you could create the opposite of that number. So the number could be 5, and then you'd have the opposite of 5, which turns out to also be negative 5. But you could have had negative 3, in which case the opposite would make it the opposite of negative 3. Okay. So what I guess I'm saying is you don't know just because it has this symbol right here, you don't know whether it's positive or negative. So you got to do a little bit more than just saying it's positive or negative. So I think changing the way you say it, if you say negative n, I need you to start not saying that, because at least if you say the word opposite of n in your mind, you might be thinking, oh, it could be positive or negative. I'm not sure which one. All right. Hopefully that gets you the right push in the right direction. I know this is not ideal to miss a day of class, and uh, it sucks because it's a day of class, and I know we had the exam planned and we were going to move forward, but I can't control the electricity, so we'll just do our best. If you have other questions, please let me know. All right, off you go.